Welcome to Study Loop.
So here we're going to choose the origin to be at the bottom of the hill, just where the incline starts. We can say that the equation of the line describing the hill we can denote as y sub 2, and this would equal x tangent of theta. Theta being, of course, the angle of incline of the hill. We can say that the equations of the motion for the object, we can say are going to be y sub 1 equaling vy initial t plus 1/2 a sub y t squared. And then we can say that x is going to be equal to vx initial t with vx initial equaling v initial cosine of theta. And of course, vy initial equaling v initial sine of theta. We can solve for the horizontal equation for the time of flight, and then insert that into the vertical motion equation. So we can say basically t is going to be equal to x divided by vx initial, which would of course equal to x over v initial cosine of theta. Now we're going to plug this t into this equation. So this t term into the second equation here. So we can say that y sub 1 would be equal to v initial sine of theta times x over v initial cosine of theta minus, we'll say, g over 2 times x over v initial cosine of theta quantity squared. And at this point, we can say that y sub 1 is simply going to be equal to x tangent of theta minus gx squared divided by 2 times v initial squared cosine squared of theta. And at this point, we can set this equal to y sub 2. So this would be x tangent of theta equals x tangent of theta minus, again, gx squared divided by 2v initial squared cosine squared of theta. And then we can say that tangent of theta minus tangent of phi, some angle, is going to be equal to gx squared divided by 2 initial squared cosine squared of theta. Let's get a new workbook here and solve for x. So x will then be equal to tangent of theta minus tangent of phi divided by g times 2v initial squared cosine squared of theta. And here, this intersection x-coordinate is related to the desired quantity d, where x is equaling d cosine of phi. So here, we can set this equal to this equation now, again, and say that d cosine of phi is going to equal tangent of theta minus tangent of phi times 2v initial squared cosine squared of theta divided by g. And we're going to solve for d now. So d will then be equal to 2v initial squared divided by g cosine of phi multiplied by sine of theta, cosine of theta, minus tangent of phi, cosine squared of theta. And in order to maximize distance, we need to set the derivative of this equation with respect to theta to 0, and then solve for theta. So we can say the derivative of d with respect to theta would be equal to 2v initial squared divided by g cosine of phi times d over d theta times sine of theta cosine of theta minus tangent of phi cosine squared of theta. And we're going to set this equal, this equals 2v initial squared over g cosine of phi, and then take the derivative of this term here. This will be, we have to use product rule. So sine of theta times negative sine of theta plus cosine of theta times cosine of theta minus tangent of phi times 2 times cosine of theta times negative sine of theta, close parentheses. And this is going to be equal, we can say this is going to be equal to 2v initial squared divided by g cosine of phi. Once again, keep the factor. And multiplied by negative sine squared of theta plus cosine squared of theta plus 2 tangent of phi cosine of theta sine of theta. And then this, again, is going to be equal to 2v initial squared divided by g cosine of phi times cosine of 2 theta plus sine of 2 theta times tangent of phi. Set this equal to 0 and solve for theta. So we can say that cosine of 2 theta plus sine of 2 theta times tangent of phi will equal 0. Therefore, theta will equal 1/2 times arctan of -1 over tangent of phi. So this would be our answer. That is the end of the solution. Thank you for watching.